Sometimes when I get an email that's really long, could be long as the neck of a giraffe, it's too long. I don't read it, and I'll just write TLDR. Too long, didn't read. Well, we've been working for 3.5 weeks to get to this point, and I hope it's not TLDR for you because this is the main point. This concept, rigid body equilibrium, is the main point of this course. It's the Chumbawamba Lollapalooza of this course. I use these concepts for rigid body equilibrium all the time in my work and my everyday life. It's static-tastic. If that all sounded a little janky, it's because I'm trying to use your special words in these videos. Hopefully you can find them all. But here's the main concept. Sum of all forces are equal to 0. We learned that in particle equilibrium, and now the new concept is sum of the moments, which we just learned how to calculate. That will also equal to 0. I don't mean to be monotonous, but again, this is the main concept. And these vectors, sum f equals 0 and sum m equals 0, mean different things in 3D and in 2D. In 3 dimensions, which we won't do that much, sum f equals 0 means the 3 force components equals to 0. And remember that a moment is a vector as well, so in 3D, sum moment equals 0 means these 3 x, y, z components of the moment are 0. We'll be doing the bulk of our problems, however, in 2D. And usually in 2D, you have x and y, or sometimes in math class, you call this the abscissa and the ordinate. But in this class, we're going to use x and y. So the x forces have to add up to 0, the y forces have to add up to 0, and the moments, counterclockwise or clockwise, will also have to add up to 0. And remember our right-hand rule to define moments when you're spinning counterclockwise, that's actually a z moment. The first step to solving any rigid body equilibrium problem is to draw a correct free body diagram. My daughter watches this show called Special Agent Oso. He's this yellow bear. He kind of looks like a panda bear, but he can solve any problem in 3 simple steps. Well, drawing a free body diagram takes 4 steps, but if you follow these 4 steps, it'll work every single time. Step number 1 is to draw a closed shape around what you're interested in. Then you look within that shape, it helps you concentrate, and redraw everything that's inside the closed shape. Draw all the forces inside your closed shape, so whatever your shape enclosed, if there are forces in there, you draw them in, and invariably this shape that you draw will cut through things and then draw in any forces that are cut by your closed shape. If you follow these 4 steps, you will always get a correct free body diagram. Let's do an example. Okay, here we have problem 4-101 that we did before. Rather than just do a reenactment of that solution, let's change this problem to just draw the FBD of the beam. Okay, step 1, draw our shape. I'm going to do that. Okay, that's step number 1. Step number 2 is to draw what's in that closed shape. We just have that beam. Let me sketch that real quick. There we go. That's step number 2. Step number 3 is to draw all the forces that are in that loop. So I see this 450 Newton force there, this 200 Newton force coming up, and also this 200 Newton meter couple in there. That's step 3. And step 4 is to draw in anything that loop has cut through. So I cut through the support at O, and we'll learn more what this support is in a little bit. But when you cut through a fixed end like that, you have this X force there that you're cutting through, this Y force that you're cutting through, and you also happen to be cutting through a moment there. So this is the free body diagram for that beam in problem 4-101. So what about these supports? Whenever you draw a free body diagram, you'll most invariably cut through these supports. What kind of forces are on these types of supports, and how do you draw them? And also I'm going to talk about what do these look like in real life. Okay, let's go through a bunch of supports and what kind of forces they put on a structure. So here's a cable, and if you cut the cable, obviously the cable pulls, so here's a force. The other thing is that the force is along the direction of the cable. And so if you notice, this angle theta is that angle theta in a free body diagram. A weightless link is just like a cable. A weightless link has to have a pin here. That means there's no moment there and no moment there. And if that's true, the weightless link also acts on the angle of the link. So this angle here is the same as that angle there. The difference between a link and a cable is a link can pull like this in tension, but a link can also push in compression. Now a cable or a rope can only pull in tension. It cannot push. The link can push or pull. It's like that mythical creature, Dr. Dolittle. Not the unicorn, it's that push me, pull me. And so that force, that animal, it was like a llama. It had two heads, and it could push or pull because it could go left or right. And so a link is like that. It can push or pull. Here you have a roller. It's drawn like this usually. Triangle with two wheels. We use a triangle usually to indicate no moment, like it's just attached a little pin there. But anyway, the key thing to know about a roller, and this one is very important, the roller is normal to the surface or perpendicular to the surface. You have a surface with the roller, and the wheels, they don't have any friction along the surface, so they have a reaction only perpendicular to the surface. This rocker, I don't know, I guess you see these. It's the same thing. It's a roller. Hey, it rolls. It only has a force perpendicular to the surface. These two are very important. I always will call them roller. And what they mean is the force is perpendicular to the surface. Again, this is really important to know. This is everywhere in statics. Okay, these reactions are on different types of surfaces. So whenever you have something resting on a smooth surface, the key thing is that the reaction will always be at 90 degrees. Or if you have a roller or a pin in a smooth slot right here, the difference for this one is that you could have a normal force going up on the roller or a roller force coming down, whereas in the previous one you can only have a normal force going up away from the surface. A smooth collar on a rod will be like this. It's the same thing. There's no reaction along the rod because there's no friction, so you could have this reaction coming up like this or down like this. These two are the same. Okay, here is another really important one, often drawn in a picture just as a triangle. There's no moment there because of that hinge, but what you do get is you get an X and a Y reaction. This one here is kind of rare. I've not really seen something like this, but there's no friction along the rod, so you can have a reaction going up actually or down. But because of that T joint there, this one also has a moment. So it has a normal reaction and a moment. And finally, we have this fixed support. This is another important one. It has all three things, X reaction, Y reaction, and a moment. So the three most important ones that you really need to know are a roller. Okay. So the roller has only a normal reaction. The next one is a pin, and that pin has an X and a Y reaction. And the last one is a fixed end, and that has a X reaction, a Y reaction, and a moment. So you can see that this has one reaction, this has two reactions, and this has three reactions. These three are the most important ones for you to know. So another thing that confuses students is this. So let me draw a beam. It's fixed on that side, maybe a roller on this side, and it has a pin in here. Okay, so what's interesting about this is that this has this reaction there. This has all three reactions. Now this has a reaction. Let's make it a roller. This one has a reaction up. However, the difference between, let's call this A and B, the difference between A and B is that here there's no moment. It's pinned and it can spin, there's no moment. Here, that's something different. There is a moment there because it's not actually hinged right there. The beam's not hinged, so there is a moment there. So at the end, when it's pinned like that, there's no moment, and in the middle, there is a moment internally in the beam. We'll talk about this later. It'll be confusing, but for now, let's just put this on the back burner. We'll come back to that later. And the main point are these three right here. You need to know a roller has a normal reaction, a pin has a X and Y, or just two reactions, and the fixed end has all three reactions, X, Y, and moment.